Hello.
Okay, I have one theorem left in the previous seminar. So I will start first. Okay, can everybody see this?
Yeah.
Oh, okay. So do you have any ideas in the last week? Anyone, any of these three? Okay, if not, I will just show you how to prove this. For the first one, we can first assume we have a simply ordered set X, and there are two elements in this set XY, with X is less than Y. So there are basically two cases. First one is if there is an element between X and Y. So in this case, we can find two neighborhoods where U1 equals minus infinity to Z and U2 is Z to infinity. So this satisfies the definition of the Hausdorff space. So by the way, do remember the definition of Hausdorff space? It basically says if we have two distinct points, x1, x2, in a topological space X, and we can find two neighborhoods, U1 and U2, where U1 intersects U2 equals an empty set. Basically, they are disjoint. So actually, for this case, we can find these two sets, they are disjoint, right? So the second case is there is no number between, there is no element between X and Y. So in this case, we can find U1 equals negative infinity to X or negative infinity to Y with where the interval is open. So similarly, U2 equals . So in this case, we can find U1 equals negative infinity to X or negative infinity to Y with where the interval is open. So similarly, U2 equals . Sorry, write the wrong way. So basically, they are destroyed. So any questions? This is the proof for the first one. Okay, if not, let's come to the second one. So for the second one, first we assume we have a product of two Hausdorff spaces, X product Y. And so we have, suppose we have two distinct points, A1, product B1, A2, B2. So basically, basically there are two cases. Either A1, it's not two cases, either A1 is not equal to A2 or B1 is not equal to B2. So we can only we can only analyze one case. So A1 is not equal to A2. Similarly, B1 is not equal to B2, just the same proof. So if A1 is not equal to A2, since it is a Hausdorff space in X, there exists two neighborhood U1, U2, where A1 belongs to U1, A2 belongs to U2, and U1 intersects U2 equals the empty set, right? So U1 product Y is open. So U2 product Y is also open, right? They are both open in X product Y. So we have it equals the empty set. So we basically find these two neighborhoods, U1 product Y and U2 product Y. Any questions?
I just have a comments on your notation. So usually we don't really write it like this. So like U1 cross Y intersect with U2 cross Y is equals to U1 cross U2 cross times Y. U1 intersect with U2 cross Y. This.
Yes. Maybe I write in the wrong way. Sorry for that.
Yeah. But I mean, this equation is not. I think this equation it doesn't really make sense. Well, although it is correct, but it's a little bit weird. Okay, but it's okay. It's okay. Yeah.
Okay. Yes. Any other comments or questions? Okay, so let's see the third one. So basically it says a subspace of a Hausdorff space is a Hausdorff space. So suppose we have a topological space X and its subspace subset Y. So let Y1 and Y2 be two elements of Y. They are distinct. And since Y is a subset of X, they are also elements of X. So since X is a Hausdorff space, we can basically find two distinct disjoint neighborhoods, U1, U2. Their intersection is empty. And where Y1 is an element of U1, Y2 is an element of U2. So by the definition of the subspace topology, there exists two open set in the subspace topology Y, where U1 prime equals U1 intersects Y. Right? So since Y1 is an element of Y and U1, so Y1 belongs to U1 prime. Yes. And Y2 belongs to U2 prime. So, and U1 prime intersects U2 prime equals. Okay, right here. U1 intersects U2 intersects Y. And it is an empty set. So let's finish the proof. Any questions? Okay, if not, I finally finished my part. So let's invite next presenter, Theodora, right?
Thank you for your part.
Yeah, anybody did any exercise of this three sections? If no, then I think Theodora you can just will continue.
I have not prepared any exercises, I think. So.
Yeah, it's okay, but yeah, I would suggest that you can try to use some exercise as well additional examples when you try to do the presentation in the future. Okay.
Okay. So my part is about continuous functions. Before I start, I want to say that I found it very long, and I'm sorry if I mess up with some place or something. I tried to prepare it the best way I can, and I hope it works. So it's part 18 about continuous functions. So we start with our definition for continuity of functions in topology. So if X and Y are topological spaces and F is a function mapping X into Y, it is continuous if for each open subset V of Y, the inverse image of V is an open subset of X. It is important to note that the continuity of F depends not only on the function, but also on the topologies of X and Y. And from there, we have the notions for continuity using the basis B. So if the topology of Y is given by a basis B, then F is continuous if the inverse image of every basis element is open. Since the open set V can be showed as a union of basis elements, and if it's open, its inverse image, which should also be open, would be the union of inverse images of those basis elements. And this union will be open if those inverse images of basis elements are open. And if the topology of Y is given by a subbasis S, then F is continuous if the inverse image of every subbasis element is open, since the inverse image of B can be presented as a finite intersection of inverse images of subbasis elements. And from there, we go to our first example. So most of us are familiar with the epsilon delta definition of continuity on R, which we study in calculus and then probably in analysis. And it's actually equivalent to our topological definition of continuity. So in example 1, we show this continuity by going from the topological definition to the epsilon delta definition and then going the other way around. So does anyone want to try to go from to prove that if one of the definitions holds, then the other definition holds as well? Okay, I will move on to the proof. So firstly, if we go from the topological definition to the epsilon delta definition, we know that for x0 belonging to R and epsilon greater than 0 belonging to R, the open interval ranging from f of x0 minus epsilon to f of x0 plus epsilon would be an open set on the range of the function. And by definition, its inverse image will be also open on the domain of the function. So the inverse image of V would contain x0. Thus, it would also contain some basis element AB about x0. So if delta is the minimum of x0 minus a and b minus x0, then for every x such that the absolute difference of x and x0 is more than delta. X would belong to x would belong to the open interval a to b, and just f of x would belong to v, or the absolute difference between f of x and f of x0 would be smaller than epsilon. And thus we get our epsilon delta definition. And then we can go the other way around from the epsilon delta definition toward topology definition. So if we have an open set A in R, if x0 belongs to the inverse image of A, then f of x0 belongs to A. And A is open, so there exists an epsilon greater than 0, such that the interval, again, like the topmost example, the interval V, which is the open interval from f of x0 minus epsilon to f of x0 plus epsilon, is a subset of A. And by our proposition, there exists a delta greater than 0, such that if u equals x0 minus d to x0 plus d, minus delta to x0 plus delta, then f of u would be a subset of v, or u, which means that u would be a subset of the inverse image of v. And we can actually present the inverse image of V as the union of all open sets YQ, and it would be open. And this, again, we have reached the topological definition of continuity. So after example 1, we have example 2, which mentions that other notions of continuity which we have met in math books before, like functions mapping from R to R squared, or R to R cubed, or R squared to R, all of the notions of continuity which we have for them can be shown that they're equivalent to our topological notion of continuity. I have not put the example on a separate slide because I think we're going to discuss example 2 more when we study metrical spaces. And our next example is example 3. So let me. So if R is the usual topology of the real numbers and RL is the lower limit topology of the real numbers, we can recall that the lower limit topology of the real numbers is defined, its basis contains all semi-closed sets of the type, I'll just draw, I'm sorry, type A to B, where A is smaller than B. So all elements of this kind are basis elements of RL. So we can see that the function which maps R into RL as an identity function such that f of x equals x is not continuous because the semi-closed interval from A to B would be open on the range, but its inverse image by the identity function, which would be again the same interval, is not going to be open on the usual topology of the real numbers. So f is not continuous. However, if we consider the function g, which maps the lower limit topology into the usual topology of the real numbers with the identity function, g would be continuous because every open set A to B from the usual topology. It can be, it would also be an open set on the lower limit topology, since it can be made by the union of two semi. Okay. It would be an open set on RL. And I don't have in my notes why this would be so. So if maybe we can, someone can help me explain why AB would be open on RL.
Maybe it's not correct, but I remember that if like for any like this open interval AB, we can find an like interval AB where it's half open, like you write in the upper half of this slide. So this one is open. So yes, and this is a subset of this open that contains this.
I'm trying to figure out a way to basically form an open interval, the open interval A to B, by either a union or an intersection of closed intervals with type C to D. Since these are our basis elements of RL, and I think every open set can be formulated as. Wait, I need to go back and see. Sorry, I didn't check this earlier when I prepared for the talk. So okay, that's confusing. I think it was, we had the thing that every open set can be presented as a union of basis elements. Am I right about that?
Yeah, I think you, well, for this, well, how to show that the open interval AB is actually open, right? I think we did this kind of problem when we introduced this lower limit topology. And Todora, you're right. You try to write AB as the union of this kind of half open, half closed interval, right? The only problem is how you can write this AB as a union of this kind of half open, half closed interval. So how can you exclude one point? Any idea?
Can we use order in some way when we do this?
That is on R, right? And R, it's a bit hard for you to use the order because it's not discrete. Two numbers in between, there will be another number. This will always be true, right? And well, maybe I can write it for you. How about we trying to write it as some kind of set like this. Can you see this is well, this is the union you want. Can you see this? I just wrote it.
Yeah.
So can you say that, well, this open interval is equals to the union of this kind of interval?
Oh, so actually it would never have A. It would always have A plus something, a little something.
Yes, so
right.
First, on this union, A will never be on any of these intervals, right?
Mm-hmm.
Because it's always A plus a little bit. So A will never be on this kind of intervals. But for any number between A, B, it will be in some of these intervals, right?
Mm-hmm.
Which means, okay, these two sets are equal.
That's such a nice way to write it.
Well, you can just imagine how you can exclude one point from this kind of infinite union, right? This is kind of a trick by taking the limit, how you can include a point or exclude a point. Okay, this is a very usual way to deal with this kind of topology problem.
Thank you.
Mm-hmm.
Okay, so now we know how we get that the open interval from A to B is also open on RL, and this would prove that the function T is continuous. And we can move on to our first theorem. So theorem 18.1 states that if x and y are topological spaces and a function f is defined from x to y, then the following are equivalent. Saying that f is continuous is the same as saying that for every subset A of x, f of the closure of A would be a subset of the closure of f of A. Then for every closed set B of y, the inverse image of B would be closed in X. And for each X belonging to big X in each neighborhood V of f of X, there is a neighborhood U of X such that f of U is a subset of V. So basically the logic which the textbook uses is we prove 2 from 1 and then 3 from 2 and then 1 from 3, and then we prove that 1 and 4 are equivalent statements by showing that 1 brings us to 4 and then from 4 follows 1. So since for this one I have used the textbook proofs. Does anyone want to try to prove them on their own before we move on to the textbook proofs?
So before you prove that, Tadaro, maybe I would like to ask you a question now, because for this kind of thing, the continuous function is very, very important in topology, because that's the reason why we want to introduce topology. We want to introduce topology simply because we want to use some, well, basic structure to characterize the continuous or continuity. Okay, so that's, well, this kind of theorems, it has a lot of statement, and it says that the following statement are equivalent. But then maybe, can we just maybe try to imagine some kind of some kind of functions that we are familiar with? For instance, how about x and y are both r? And could you find some functions f which is continuous in the usual way from r to r? And we know that, okay, the inverse of this map, if this map is continuous, then it's really good because it can, the inverse of this map can map an open set to an open set, and by 3, it can map a closed set to closed set. Okay, this is very good. But now, why we are interested in this inverse, this kind of F inverse, not F? 2 and 4 just tell you something, right? The reason is, if you try to look at this F itself, and we try to study this topology, then what you can see is, okay, if you have a closed set, then, well, F of this closed set may not be closed. And for 4, F of an open set may not be open, right? It just says that, okay, F of this closed set is actually, well, a subset of the closed set. And F of this open set is a subset of the open set, right? So could you give us some kind of examples, like the real functions, such that these functions, you can see that the inverse of these functions of a closed interval is closed, of an open interval is open, but the map, it can map an open interval to something not open, or maps a closed interval to something not closed. Is that okay? Okay, maybe write some kind of functions and see what kind of image of an open interval of this function is, our closed interval.
Okay, I will try to think about a function which would do
you
that.
can write it randomly. It's actually not so hard to see. Well, most of the functions, you can see that the image of this function of an open set may not be open, something like that. Okay.
Okay, so if we have f of x equals 1 over x,
okay,
and then okay, so I have to think. I'm sorry. So the inverse would be okay. So
it seems that 1 over x is not as good as you want, right? The reason why 1 over x is not as good as you want might be, it's actually an injection, right? So basically, if you have some open interval, then it will somehow maps to an open interval, right? So that's closed. It's actually monotonic, this function, right?
mm-hmm.
Maybe you want some function which is not an injection. Can you write down a function which is not an injection? from R to R?
Okay, so
yeah, this one is enough, right? This one is very, it's a first function that we know that is not an injection, right?
yeah.
But we know that it is continuous. So the inverse of this function must be very good. However, can find, for instance, an open set such that the image of this open set is not an open set.
So if we consider the open set of the form minus A to A, then can we say that its map would be 0 to A squared?
Yes, that could be an example. Yeah, you can see that, okay, at least it maps this open interval to an interval that is not open.
Can we do the same thing for a closed set on this function? Or to find a closed set of whose image is not closed?
Yes, we could, but I think this may not be a good example for this closed set because it's I think it's a bit hard to well, this is not a good example, I think. Is it? Let's see. So for instance, yeah, probably it's not a good example because then you'll find that for any subset of R, well, this A is a subset, then FA bar is actually equals to FA, and you take bar, right? So for the second statement, it's always equation. Is it? Am I right?
I think so.
Probably yes, right? Probably yes. Yeah, I think so. Then maybe if we want to find some functions such that the second part, the second statement is really this is really a subset, right? FA bar is really a subset of FA bar. Well, what kind of function we could find? Do you have any idea? So how about, say, arctangent? I think arctangent could be, I think arctangent might be an example, right? Because for arctangent, for instance, it can map 0 to plus infinity, which is a closed interval, right? this closed interval, it maps this closed interval to an open interval, right? To a half open, half closed interval, 0 to half pi. Am I right?
Mm-hmm.
Because the limit, well, this limit, it can only take the value at infinity. However, the closure of this 0 to infinity is still 0 to infinity, right? We cannot add infinity as a number to this interval. Is that right?
Yeah.
Yeah. So when you see this kind of theorems in the textbook, try to imagine, well, what kind of functions or what kind of image that this theorem trying to tell us, right? That would be very interesting and that would be very important. Otherwise, you just see this kind of theorems as quite abstract and very boring. Okay.
Okay, I will try to do it.
We may see more examples later. Okay, when you talk about the homomorphism, I think a little bit later, right? So when you try to learn this kind of thing, this topology stuff, trying to understand all this kind of theorem statement by examples. This is very important. Otherwise, it's really abstract and it's really hard to understand. This is very important when you try to learn a topology, okay, a topology course.
Okay. So maybe I can move on to the proof now. So when we prove that 2 follows from 1, or that from the fact that f is continuous, it follows that for every subset A of x, f of the closure of A is a subset of the closure of f of A. Can do it in the following way. So if f is continuous, then A is a subset of x and little x belongs to the closure of A, and V is a neighborhood of f of x. And the inverse image of V would be an open set on X, and it would contain little x. And by theorem 17.5a, which I need to find my notes. Okay, which we can find on page 96, and it states that if A is a subset of the topological space X, then X belongs to the closure of A if and only if every open set containing X intersects A. So as we see that the inverse image of V should intersect A at some point Y. And from this we get that V would intersect f of A in the point f of y, and again by theorem 17.5 we see that f of x belongs to the closure of f of A. And then when we go on to prove 3 from 2, which is we prove from we know that for every subset A of x, the closure of f of the closure of A is a subset of the closure of f of A, and we have to prove that for every closed set B of y, the inverse image of B is closed in X. So let us consider a set B which is closed in Y, And if we have A which equals the inverse image of B, we know that f of A equals f of the inverse image of B, which is a subset of B. One like we talked just a little bit earlier. And thus, if X belongs to the closure of A, then f of X would belong to f of the closure of A, which is a subset of the closure of f of A, which is a subset of the closure of B, which would equal B since B is a closed set. And okay, so the proof from this point goes on that f of X is a subset of B, and thus X belongs to the inverse image of B, or the closure of A is a subset of A, and by definition A is a subset of the closure of A, thus A equals the closure of A, or A is a closed set. A little point on which I was perplexed when I was reading this was about this relation. So it might be a really stupid question, but I did not understand quite well why the closure of f of A is a subset of the closure of B. So maybe someone can help me to figure it out.
Is that because FA is a subset of B? I don't know.
How do we prove that the closure of a subset is a subset of the closure of the original set?
Since FA is a subset of FA closure, and FA is a subset of B. B is a subset of D closure. So I may write somewhere. If F
think that we need something in addition to this set theory proof, because from these three it doesn't directly follow that this set is subset B, the closure B. And I think I'm just missing a point somewhere which would point out why from this and this and this it follows that this is true. But I think we need an additional point, because just by using set theory, this is not. We can have sets for which A is a subset of B and C is a subset of D, and A is a subset of C, but B is not a subset of D.
Well, I think you may forgot one thing, right? We have B is closed.
Mm-hmm.
Yes.
So which means B is actually equals to B bar.
Yes.
Which is here, right? I think, Todara, you have questions about why A is a subset of B, then A bar is a subset of B bar. Is that correct?
Mm-hmm.
Yeah. So this can be proved by the definition of the closure of a set. If you have a set, then what is the definition of the closure of this set?
It's the intersection of all closed sets that contain it.
Yes, that's right. Then if you have, for instance, let's say you have C and D. C is a subset of D, right? Then the closure of D is equals to the intersection of all this kind of Dj, such that the Dj contains D and Dj closed, right?
Mm-hmm.
And the C bar is equals to the intersection of Ci, where Ci is closed and Ci contains C bar,
Mm-hmm.
right? So which means, okay, so this Dj, some Dj must be this Cj, or well, Ci, right? Because it also contains C and it's also closed. So which means here, this intersection, you have more set. Okay, so this intersection, you can write it into two parts, and such that it's equals to the intersection of Dj intersect with something else. Right? Because Dj must be some Ci, as we said. Which is why you can see that C bar is a subset of D bar.
Yeah.
Okay.
Yeah, I understand it now, and okay. I just failed to make the last connection about the intersections.
Yeah, this is very well. This is a very important property of the closure of a set, which is a closure you can just take it freely. If you have this well less or equal to, you can also, or the subset, or you can always take this kind of thing. It's fine.
Okay, thank you. And okay, so I guess we can move on to how we get one from tree. So again, tree states that for every closed set B of Y, the inverse image of B is closed in X, and one states that F is continuous. So if V is an open set of Y and B equals Y minus V, this would make B a closed set on Y. And the inverse image of B would equal the inverse image of Y minus the inverse image of V, which would equal X minus the inverse image of V, which would which would be a closed set on X as well. So yeah, and since we know that, oh, wait, excuse me for my last sentence. I was not following what I wrote on the screen. And basically, B is a closed set, and the inverse image of B is a closed set, and then we get that it equals X minus the inverse image of V. This would make the inverse image of V an open set. And since B is an open set as well, then F would be continuous. And then we go on to prove that 4 follows from 1. So 4 states that for each little x in each neighborhood V of f of x, there is a neighborhood U of x such that f of U is a subset of V. So if little x belongs to x and V is a neighborhood of f of x, then the set U, which equals the inverse image of V, would be a neighborhood of x such that f of U is a subset of V. And then if we go the other way around to prove 1 from 4, if we have V as an open set of Y and X belonging to the inverse image of V, then f of X would belong to V. And by proposition 4, there would exist a neighborhood Ux of X such that f of Ux is a subset of V. And then Ux would be a subset of the inverse image of V. And since the inverse image of V can be expressed as the union of all open sets Ux, then the inverse image of V is an open set itself, and continuity has been proven. So now we go to our next part about homeomorphisms. So we have two definitions. If X and Y are topological spaces, and F mapping X into Y is a bijection, but F and its inverse function mapping Y into X are continuous, then F is a homeomorphism. And then if X and Y are topological spaces and F mapping X into Y is a continuous injection, then Z, which equals F of X, would be a subspace of Y. And F prime, which maps X into Z, is a homeomorphism, then F mapping X into Y is a topological embedding of X in Y. So topological homeomorphism is a concept which is similar to algebraic isomorphism. So it would preserve, when we have a homomorphism, we expect to see the topological properties to be preserved in how do I say it? It just preserves the topological properties of, I guess, the topological space, which is the domain of the function, when it maps it to the range of the function. And yeah. So honestly, when I was reading about the homeomorphism, I understood the concept as a really as an analogical concept to isomorphism, but the thing which I was thinking about examples of topological properties which could be preserved. So maybe I did not come up with any good example. So can someone help me to think of an example of a topological property which can be preserved in homeomorphism? one thing which I thought about analogically to algebra is order. So can we say that a homeomorphism would preserve the order on X when it goes to Y?
Well, is order a topological property?
I'm really not sure about that. I don't.
Yeah, you see, we learned the order in set theory, right?
Yeah.
Not in this course, right? So probably is.
Sorry, Professor, I cannot hear you.
Hello. Sorry, I was just kicked off from this room.
Okay.
Yeah. So, what kind of property or what kind of terms we've learned from this topology course, and based on this topology we define. For instance, we know that, okay, if you gave me a set and define the topology on this set, we can define the open set, right? So the homeomorphism maps an open set to an open set.
Yeah.
And it's one-to-one corresponding, right? And also it maps a closed set to a closed set, right? It is also one-to-one corresponding. And moreover, for instance, if you want to see what kind of property it will conserve or preserve, I think in last week, or well, Zikang just mentioned Hausdorff space, right? A topological Hausdorff, and something happens, right? And then suppose we have two topological space, and you have a homomorphism from one to another. If we know one of them is Hausdorff, then we know both of them are Hausdorff, right?
Yep.
So everything based on the definition of topology, or based on the topology of a space, all the properties, as long as you have this homomorphism, it can preserve, right? But it has to define based on your topology of this set. And another very, at this moment, you cannot really understand it, but very interesting example is, now you may be able to understand why we say that, okay, when you talk about this topology, you always try to imagine something like the dirt. You play with the dirt, right? Or you play with a donut. Why we say that a donut and a cup, a drinking cup, are the same? Well, with handle are the same. Why we say, for instance, you have a donut. This is well, I didn't draw it very good, but why you say this donut topologically is the same as a cap with handle. Why do you say that? It's just because we can try to play with some part of this donut and try to make it the same as this one, and then this hole you cannot change, and it becomes the ear of this or the handle of this cup, right? So which means you can find a homomorphism from donut to this cap. Okay.
Mm-hmm.
Or if you want, you can always play with a ball and maps it to something. You cannot map a ball to a donut, but you can map it to I don't know, like whatever, something. Okay, I try to draw a door or a body, but I'm not very clear. But you can try to play with this ball and try to make it look like a human, right? So this kind of thing is also a homomorphism. It's continuous. You can make it continuously change from a ball to a body. But you cannot make this ball continuously to a donut. You have to break something when you try to make a donut. Okay? Which is why we are interested in this topology.
Thank you for the examples. So we have several examples from the book which go over what is a homomorphism. So the first one is example 4, and if we have the function f which maps from R to R such that f of x equals 3 times x plus 1, and then g which maps R into R such that g of y equals 1/3 of y minus 1, we can see that g is an inverse function of f. It's in the algebra right here. I don't think I need to read it. And f is a bijection. And if we use calculus, we can prove that both f and g are continuous. So since f is a bijection and both f and its inverse function are continuous, f is a homomorphism. And then we have another example. If we have the function f, which maps the open interval -1 to 1 into R, such that f of x equals x over 1 minus x squared, f would be a bijective order preserving correspondence, and its inverse function would be g, which maps R into the open interval -1 to 1, such that g of y equals 2 times y over 1 plus square root of 1 plus 4 times y squared. And since f is order preserving and bijective, f would map a basis element of the order topology of the domain onto a basis element of the order topology of the range. And the same goes for g, and thus f would be a homeomorphism. And we have, in our next example, we consider a bijective function which is continuous without being, I'm sorry, I see someone is writing in the chat. Okay, sorry. So yeah, a bijective function can be continuous without being a homomorphism if its inverse is not continuous, which is similar to the function g, which we considered in example 3, where we mapped RL into R. Another example would be if we consider S1, which equals to the collection of x cross y, such that x squared plus y squared equals 1, which would be the unit circle considered as a subspace of R squared. And then we consider the function f, which maps the semi-closed interval from 0 to 1 to S1. And it is defined by f of t equals cosine of 2 pi t and sine of 2 pi t. Then f would be continuous since each of its component functions is continuous. But the inverse of f is not continuous for any set u of the type semi-closed interval 0 to k, where k is more than 1, since the point p, which equals f of 0, would not belong to any open set v, which belongs to R squared, such that the intersection of v and S1 would be a subset of f of u. And in example 7, we consider again the same function, which we just increase the range. Instead of S1, we keep the same rule, but we map the semi-closed interval from 0 to 1 to R squared. And thus we can see that an injective function may not always be an embedding. So we saw that G is not a homeomorphism, that F in the previous example, which maps the semi-closed interval from 0 to 1 to the unit circle, is not a homeomorphism. Thus, even when we expand the range, we would not get an embedding, since we cannot have an embedding without a homeomorphism. And the next part of the chapter is about constructing continuous functions. And okay, so we have theorem 18.2, which tells us several rules for constructing continuous functions. So if x, y, and z are topological spaces, our first rule is if f mapping x to y maps all of x into the point y0 of y, then f is continuous. Okay, I'm sorry. Apparently I have a bad one in the presentation. I'm sorry. And our second rule is if A is a subspace of X, then the inclusion function J, which maps A into X, will be continuous. And our third rule is F maps X into Y and G maps Y into Z, they're both continuous, then the composite function G after F, which maps X into Z, would also be continuous. And so our proof goes on like, for the first one, if we have an V as an open subset of Y, and we have Y0 belonging to Y to V. I'm sorry for the typos. I will fix the presentation and send it without typos later. I'm sorry. So if Y0 belongs to V, then the inverse image of V would be X, which is an open set, and the topology of X. And if V does not contain Y0, then the inverse image of V would be the empty set, which is also an open set. Thus, F would be a continuous function. And as for B, which states that, just a sec. it states that if A is a subspace of X, then the inclusion function J, which maps A into X, is continuous. If U is an open set in X, then the inverse image of U, which equals A intersecting U, would be an open set in A by the definition of subspace topology, and thus J would be a continuous function. And then for C, which states that the composite function of two continuous functions is also continuous, we consider W, which is an open set in Z, and its inverse function, function on Y is, okay, honestly, I just don't know what's the correct way to read this, so I don't stumble across it, because I can say G to the power of -1 or something like that. So what other ways there to read it besides the inverse image of W? How do I specify that it's the inverse image of W by the function G? Hello? Sorry, can you hear me? I cannot hear anyone right now.
Yes, we can hear you.
Oh, okay. Okay, so okay, anyway, I guess I'll figure out this later. So the point is that the inverse G inverse of W would be an open set in Y, and then the inverse F inverse of G inverse of W would be an open set in X by definition. But we also know that the inverse of F inverse of G inverse of W would be the same as the composite of G and F inverse of W, and thus we have that the inverse of the composite of G and F of W would be an open set on X. So the composite function of two continuous functions would also be continuous. And then we have 3 more rules by which we can construct continuous functions. So our first rule states that if F mapping X into Y is continuous, and if A is a subspace of X, then if we restrict the domain of F to A and keep the mapping, the same function with its restricted domain would be continuous. And then we have in E, we considered if we have a function F which maps X into Y, which is continuous, it basically says that if we expand or if we restrict the range of the function, it would be continuous again. So if Z is a subspace of Y which contains F of X, and if G which maps X into Z, then G which maps X into Z would be continuous. And if Z is a space having Y as a subspace, then H mapping X into Z, which would technically expand the range of F, would also be continuous. And our last rule says that the function F which maps X into Y is continuous if X can be written as the union of open sets U alpha, such that F restricted, when the domain of F is restricted to U alpha, the function is continuous for each alpha. So our proof for D, which was for when we limit the domain, states that the function with restricted domain is the composite of the equation function J, which maps A into X, and then of F, which maps X into Y, and both of them are continuous, thus the restricted function would also be continuous. And then for E, we first consider the case where we restrict the range. So if B is an open set on Z and B equals the intersection of Z and U, where U is an open set in Y, then the inverse image of Z intersecting U would be the same as the inverse image of U, which would equal the inverse image of Z intersecting U, which would equal the inverse image of, I could have probably made a better job by pointing out what is F and G right here in the proof, not only in the condition above. So in order to keep, in order to not have any ambiguity, I will write down that F maps X into Y, and G maps X into Z. So, and Z is a subspace of Y. So that's how we get that. If B is an opposite on Z, then B equals the Z intersecting U, some U, which is an open set in Y, and the inverse image, inverse F of Z intersecting U would equal inverse F of U, which would equal inverse G of Z intersecting U, which would equal inverse G of B, and thus it would also be open, and since it equals inverse image of U, which is open. And then when we go the other way around, where wait, this was the one where we expand the range. When we restrict the range, I think, okay, so then in this case we have H, which, okay, so sorry, in this case we have H, which would map X to Z, and Y is a subspace of Z. So, okay, this is the case where we expand the range. And H is the composite function of F mapping X into Y, and then the equation function J mapping Y into Z, which are both continuous. So H is also continuous. And then for the last part, for part 6, so it states that the map F which maps X into Y is continuous if X can be written as the union of open sets U alpha, such that when we restrict the domain of F to U alpha, for every F with such restricted domain is continuous for H alpha. So we can construct X as the union of all sets U alpha, where U alpha is an open set on X. And then if V is an open set in Y, the intersection between the inverse image of V and U alpha would equal the inverse of F of V when the domain is limited to U alpha, which is an open set on X. And this, going back to this part, we can say that the inverse image of V would be the union of all such inverse images. Okay, I honestly, I'm confused about how to read this thing in English. So it's the union of all inverse images of V by the restricted, okay, so it's the union of all F limited in U alpha inverse of V, where when we use the union, we technically go back to the entire set. So, but still, since each of those restricted sets, it would be each of these sets is an open set. So their union would be also an open set. And this is how we get that the inverse image of V would be an open set and F would be continuous. And after this theorem, we have theorem 18.3, which states that if X equals the union of A and B, where A and B are both closed in X, and if F maps A into Y and G maps B into Y, and F and G are continuous, and F of X equals G of X for every X belonging to the intersection of A and B, then F and G combine to give a continuous function H, which maps X into Y, defined by setting H of X equals F of X if X belongs to A, and H of X equals G of X if X belongs to A. So this is an example. This is technically, we can imagine this is a piecewise function which is continuous, and we have an example for this later in the slides. For piecewise functions, we have piecewise function which is continuous and a piecewise function which is not continuous, and we'll see how this relates to it. So the proof for this theorem goes like this. So if C is a closed set in Y, and the inverse image of C equals the union of the inverse image of C by F and the inverse image of C by G, and both F and G are continuous, this by theorem 18.1.3, which states that, as we just read a few minutes ago. Okay, I'm just seeing through my notes to state exactly what the theorem said. So it says that for every closed set B of Y, the inverse image of B is closed in X. If and this is equivalent to the statement that F is continuous. And okay. Usually when I point to theorems. I put the page number in my notes so I can point out to that, but this time I didn't do it. So basically by theorem 18.3 and theorem 17.3, which says that if y is a subspace of x and a is closed in y and y is closed in x, then a is closed in x. Thus, the inverse image of C by F is closed in A and also in C since A in X, since A is closed in X. And the same goes for the inverse image of C by T, which is closed in B, and B is closed in X, thus it is closed in X. And thus their union, which is the inverse image of H, is closed in X, and H is continuous. And we have in example 8, we consider 3 piecewise functions. So for the function h of x, which is defined as it equals x if x is less or equal to 0, and it equals x over 2 for x greater or equal to 0. H would be continuous since both of the piecewise functions are continuous and they agree at their meeting point. So their graph would look something like this. And then for k of x, we have k of x equals x minus 2 for x more or equal to 0, and x plus 2 for x greater or equal to 0. And we know that even though both of these functions are continuous, they don't agree on their meeting point. Thus we have for x equals 0, k of x, x equals 0, k of x can be both minus 2 and plus 2. So k does not actually define a function, thus it cannot be continuous. And in our example L, which we still keep the same piecewise functions, but we changed the domains. So L of x equals x minus 2 if x is more than 0, and it equals x plus 2 if x is greater or than or equal to 0. However, we have to L would look something like, I think what it would look like. So it would look something like this. Okay. And since this interval from minus infinity to 0 is closed, even though both of those functions are continuous by themselves, we cannot apply theorem 18.3, since it applies only if the two functions are defined into closed sets. Here we have an open set and a closed set. And after example 8, we have theorem 18.4, which says that if x equals the union of a and b, where a and b are closed in x, and f maps a into the product of x and y, given by the equation f of a equals the point f1 of a and f2 of a, then f is continuous if and only if f1 which maps a into x and f2 which maps a into y are continuous. We call f1 and f2 the coordinate functions of f. And here's a proof for this theorem. So if we remember from when we talked about product topology, we had the two functions p1 which maps x cross y to x, and pi2 which maps the product of x and y to y, and we called them the projections into the first and second factors, and they are continuous. And we know that for each little a belonging to a, f1 of a equals pi1 of f of a, and f2 of a equals pi2 of f of a. So let us first start from the fact that f is continuous. In this case, f1 and f2 are composite functions of two continuous functions, and thus they are continuous. And if we start with f1 and f2 being continuous, then if we consider the u cross v as a basis element of x cross y, then f inverse of u cross v would equal the intersection between f1 inverse of u and f2 inverse of v. And since both of these sets are open, their intersection would be open too. And thus the inverse image, f inverse of u cross v would be open, and f would be continuous. And I think there was one last example. It was example 9. It basically mentioned that when we prove in calculus that this type of functions where f of a equals f1 of a, this set of functions which we formulate like this. We've met before several such functions defined in calculus, like on R and R squared. It's just the continuity which we defined in them is a special case of this notion of continuity. And I think that's about it.
Sorry, I haven't prepared chapter 19 yet. So are we going to do the exercise now, or?
Do you want to take 10 minutes break and then continue with some exercises?
Yes, okay. Maybe.
Okay. Then see you in 10 minutes.
I think it's time to be back, right? So do you guys want to do some exercise?
Yeah, but Theodora is living, right? And
where is Theodora? I think she just left and well, I don't know.
then should we end this meeting now?
Okay, so anyway, since we only have 2 people here, so maybe we will continue on Friday, right? This Friday. So don't forget to finish your part. So Friday, Holly, you will do the presentation, right?
Yes.
And who else? After you should be Aya, right?
Yes.
Okay. So don't forget to come and don't forget to spend some time on preparing this kind of things. As I said before, I think for one presentation, you may need like at least 10 hours in order to prepare it. So give yourself enough time, okay?
Okay.
So I think I will see you on Friday. See you then.
And
Okay, thank you, Professor. See you.